So now we switch gear and talk about the second algorithmic technique I want to cover this week, which is meet in the middle. So this is a technique that trade off memory for speed. I guess that's a very common idea. A lot of data structure idea is trade off memory for speed. So in this particular case, we store intermediate result, which sometimes can cut off the runtime by taking a square root, by paying, but we are paying the overhead, we are paying the memory. We basically store intermediate result to make the overall computation faster. And this is used in, so for example, actually my first encounter with this meet in the middle concept is actually studying the security of multiple layer of symmetric key encryption. So some of you might heard of triple DES. So why we need triple DES instead of double DES, that has something to do with this meet in the middle technique. So because of the meet in the middle technique, double DES doesn't provide a really additional level of security, assuming there's enough storage, but triple DES does. And so here, the first thing we want to talk about is actually running a warm-up. So here, for this problem, we actually don't need a meet in the middle. But I want to, so it's really when we reach 4 sum, we need the meet in the middle. But I think it's nice to cover 2 sum and 3 sum and then see how 4 sum evolves. So we actually have a warm-up problem for this problem itself, which is a warm-up problem. So I assume that you are familiar with 2 sum, so which can be solved in linear time using a hash set. So you scan through the integer in the array. Then you check whether the number you need to reach the target is in the hash set, and after checking, you put yourself in. So that solves it in linear time. When we were talking about 2 pointers, we also look at this 2 sum 2 where the input is sorted. So in this case, we just keep 2 pointer at the 2 end, and then we move them based on whether the sum of the 2 number is less than or greater than the target. So if you are given an array that's not sorted, but you are given the possibility to sort it, then to modify the array, then actually this is a better approach than using hash set. So even though asymptotically this will take in log n, sorting take in log n, and asymptotically using the hash set that takes linear in n, this is faster because the hash set actual constant factor actually is pretty big. So here we want to look at the 3 sum. So we are given an array of n integers and we are given a target. We want to find 3 integers here so that they sum to be closest to target. So when we find it, we return the sum of the three integers. So here, for example, if we are given these 4 numbers and our target is 1, then the closest sum we can reach is 2 by taking these 3 numbers. So of course, if we are allowed to only take 2 numbers, we can take these 2 and we can actually get 1. But if we want to take 3, then this is the closest. So anytime if we have -4, then the largest we can get with -4 is -1. So that will be distance 2 away from the target. And here we can get distance 1 away. So encourage you to pause the video and think about how to solve this problem. So how do we do it? Well, brute force, we can try all combination of 3 elements. So that will take n cube time. But these problems can be solved using n square time by first sorting the array. Then we can loop over the first element and see whether there exists 3 elements with that one as the smallest one to to get the closest to the 3-sum. Once we fix the first element, then the problem become a 2-sum problem, because we have a target, we fix the first element, we know the target for the other 2 elements we need. We can solve 2-sum closest in linear time using the two-pointer technique. So we scan, well, we remember what is the best we have achieved so far, and yeah. So this is we use 2 pointers. If we get 2 number that's less than the target, then we know we cannot get anything better by using AB, because all the other things we haven't looked at are going to be smaller than AE. And similarly, if this is greater than target, we'll move the right pointer. So if this is not familiar, then you should revisit the two-pointer technique lecture. Okay, so here's my C++ code for 3-sum closest. So again, if you're not familiar with C++, it's not that different from Java. So you just focus on logic here, which is pretty much the same whether we are writing in C++ or Java. So we sort the array where we store the numbers, and so we store the best gap we have achieved so far, which is initialized to the maximum integer, and then we loop over all possible first element, I, and then the beginning and end are set to be the element after this and the pointing to the last element, and we will keep going until the 2-pointer collide, in which case we know we are done. We have looked at all possibilities, and we look at the gap we get by using the 3 numbers. If the absolute value of this gap is less than absolute value of the best gap, then we remember this gap. So this is a better solution than what we remember before. And then we update the 2-pointer. And when it equals, then we know we have reached the target. So it's not possible to do any better, so we can just simply return the target. And otherwise, when this loop all finishes, then we know the answer is the target plus the best gap, because that's what we can achieve. So that's it for this. Again, that is only warm up. We haven't used meet in the middle technique yet, but for the next one we will be using it.